Good evening and welcome to OTF Connects, day 2 of our new fall season, and we are welcoming Brian Aspinall tonight to do an awesome workshop called Hacking the Classroom. Don't you just love the title? It's motivating right off the top. Brian's website says that he is a teacher, a speaker, a coder, and a maker, and I think we're going to see all of those sides of Brian tonight in this session. So I'm going to turn things over to him and turn my mic off. Welcome, Brian. We're excited to be here with you.
Thank you, Susan. How's my audio?
Awesome.
Oh, good. Okay. We already had a question there. We haven't even started yet, and people are eager to ask questions, so that's great. I think everyone's got a good sense of how these tools work, so fantastic. As always, it's interesting to speak into a microphone and stare at a slide that you made and hope that people are engaged, you know, on the other end, and you're not just making small talk and jokes for your dog in your room. So it's an interesting dynamic from my perspective, but please feel free to have a conversation in the chat. It's often tough for me to keep up with the chat, but I do like to go back through it after the fact. I encourage you to do a back channel chat on Twitter so that I can follow along there and reach out to you after the fact in the next couple of days, or if you have further questions there. So if you're not on Twitter, I highly recommend that you jump in there. There's lots of good things happening there. So totally cool to see so many people here from Superior Greenstone. I think they've earned a good gold star from the province of Ontario and the OTF session. So kudos to you folks. But for everybody, you know, there's 30 people here, passionate educators from Ontario, that are willing to, you know, take a risk and explore something new, because we're here to talk about coding, and that's incredibly intimidating. And I will say that myself, being an avid coder, that coding is absolutely incredibly intimidating. So before I jump into it, I am incredibly curious. Green check mark. Yes, I have tried coding before, even in the simplest form, or red X. I am here because I have no idea what you're talking about. And I know that we learned earlier that you cannot see the tally, so the majority of you have coded before. So I'm going to clear this, and I'm going to ask again. Green check mark if you have at least done the hour of, sorry, let me rephrase that. Let's say red X if you have done the hour of code, and green check mark if you've gone further. And I see Sarah has a question. Under your name, Sarah, on the left side, you'll see a smiley face and then a person with an hourglass that lets you alert us that you're away. And then to the far right, there is a checkbox there where you can choose green or the red X. So it looks like a lot of you have experienced coding beyond the hour of code, which is great. And a few of you here have done the hour of code, which is also a great step. So I'll try and sort of tweak this webinar as we go to make sure we can get something for everybody. So I always like to ask that question at the beginning so that we can sort of edit on the fly, if that makes sense. Before I jump into the coding piece directly and the computational thinking piece directly, I have renamed this as Hacking the Classroom, which I know, same content as I had planned. It wasn't something that was posted on the OTF website, but I thought it was a great play on words, and we can talk about how we can sort of rebrand or look at lessons, traditional lessons, things we've done in our classrooms already, but through a different lens. Okay, I want to sort of highlight activities that I've always done, you know, as a traditional teacher, as a progressive teacher, and sort of explore how we can look at math and literacy sort of through a computational thinking or computer science website. I'm going to try and do application sharing right from the get-go because I know this is the second OTF event of the year, and we're going to push it to its limits. So I'm going to try and share my yeah, Susan, thanks. Oh, good. Here we go. So let me know if you can see my browser. Right now, I think you will see a black box because I have Blackboard open. But if you could just, if you raise your hand, I hear the ding. So if you could raise your hand that you see the Province of Ontario, September 2016 mandate letter, education. I hope you hear all those dings too. Okay, there was a whole variety of dings there. So This is black box. This is Google Chrome. One more ding. Awesome, here we go. Okay, this was sent September 2016 from Kathleen Wynne to our minister, Mitzi Hunter. And it's a pretty in-depth document that I'm happy to share with you after the fact. But it talks about math, and it talks about our new math strategy in Ontario and having math, what's the word we're using? Those math, you know, the math specialists in our schools, right, where we're teaching an hour of math a day. Okay, well, if I just do a quick Control F on this web page and I type the word coding, you'll notice it's actually made an appearance. And as far as I'm aware, this is the first time we've seen something like this come through in the province of Ontario. So as we continue to implement the renewed vision for education in Ontario, we are going to complement Ontario's math strategy, develop a strategy to provide students with exposure and access to science, engineering, and technology fields that consider opportunities for computer coding. So the STEM movement, the computational thinking, the coding piece to support numeracy as well as literacy, is we're on the cusp of seeing it happen here in Ontario. It's happening in British Columbia. British Columbia has introduced a new curriculum document this year. This is just for your own general knowledge. Grades 6, 7, and 8 in the province of British Columbia have a new computational thinking / coding document that's happening in pilot schools this year and is mandated across the province by 2018. So they're setting the bar, and the rest of the country is sort of watching how this unfolds. And obviously you folks are all here because you're interested and you're passionate about it as well. So that's fantastic. The next article, my Twitter blew up today. The Globe and Mail, there was an article from Melissa with Ladies Learning Code, and she had written to the Globe and Mail about we need to teach 10 million Canadians to code or we're going to get left behind. And I feel like every person in the province tagged me in this article. It's a fantastic article in today's Globe and Mail. And if you just open it on Google and have a quick search, you'll be able to see that. So I wanted to share that. That came through today. And that's about Canada, right? Not Ontario, but Canada. Lastly, before I hit my slides again, I've been starting to use the hashtag CT Mindset. It stands for Computational Thinkers Mindset. And what I want to do is sort of engage teachers and engage students to think through this computational thinking lens. And I'll sort of explain what that term means. But I've coined the hashtag so that we can sort of follow what we're doing in math here in Ontario and beyond. So feel free to tweet tonight. Feel free to use that hashtag. Feel free to tag me in it. I'd love to come back and have further conversations with you at a later date. Okay, I'm going to head back to Blackboard, and I'm going to try and shut that off so that you don't see a black box. Which is going to be a challenge by the looks of things. Okay, here we go. There we go. Give me a ding. Are we back to slides? Can you raise your hand if we're back to slides? Perfect. I love that tool. Okay. It worked, Susan, it worked. We should write that down. Make note of that. It worked. CT Mindset. Jamie set it up on TweetDeck. Love it. Love it. I'm so excited. Okay. Let's move forward. So what exactly is coding? Why are we here? I would tell you if I could advance that slide. We seem to have a whole variety of blank slides. Just jump ahead. Here we go. Okay. What is coding? So coding is a set of instructions that tells the computer how to perform a task. And if you think about it from a language arts lens, it's something we've been doing for a long time. We've been teaching our students how to write procedures. Okay, so where I'm from in my school board, procedural writing is a form of writing that we actually we teach, right? And it's something that we explore in science classrooms all the time. We follow procedures, we create procedures when we're trying to set up science experiments. So coding is no different. It's a set of instructions that humans create to tell the computer what to do. Because really, computers are dumb. They don't do anything until you actually tell it to do something. So I want to start by looking at a few examples of things that we already do in our own classrooms. So let me back it up a little bit. I have to tell you a story from 10 years ago, because this is how I started on the journey that I'm on today. So 10 years ago, I had students approach me and say they wanted to code a game. Now, I had showed them a little bit of coding and computer science in my classroom, having studied it myself. And I was new to teaching back then. And Scratch, the application Scratch, which I'm sure many of you are familiar with, was brand new. It actually came out in 2003. So we're going back to about 2005, where the tool itself was brand new. And I was learning the tool. I understood the fundamentals of computer science, but I had a group of boys approach me and say, we want to code this game. And I said, okay, pitch it, you know. Pitch it like Dragon's Den. We didn't have Dragon's Den then, but give me this pitch. What does this look like? And they said, it's so obvious, Mr. A. It's so obvious. We want to code the pooping baby. And I laughed, and I thought for a second. I thought, okay, Twitter and YouTube and social media was blocked in those days. So what's the appropriateness, right, around coding the pooping baby? And I thought, nobody has any idea what we are doing at this extracurricular club, right? We're doing this thing after school, and we're talking coding in 2005 with grade 7 and 8 kids. So nobody has any idea what we're doing. So I said, yeah, we're totally going to create this thing, because if you have an idea and you want to run with it, I am completely motivated by this process. When I reflect on it now, I feel like, in a way, I was exploring Genius Hour, and I was exploring passion projects with these kids in an after-school setting more than a decade ago. But what's so powerful about this story, and I know that because we're on a webinar, you see a still image, but picture this baby. So this baby slides back and forth across the top of the screen, and poop missiles shoot at random from the baby, and you as the player of the game have to catch those poop missiles at the bottom of the screen. So that blue thing, that blue bar on the TV there, that would be kind of like your paddle, okay? Now, I said to these students, I said, how did you make the baby move to the left? Now, keep in mind, I'm actually exploring Scratch for the first time. I didn't know Scratch as a tool. I did study computer science, but I'd never seen the Scratch application. So they said, well, it was so easy, Mr. A. We made the baby move -1 step. And so I tried it myself, and the baby went plunk, right, and just moved 1 step to the left and then stopped. And I said, how did you make the baby move to the left forever? And they said, well, that's simple. We put it into a loop, and we told it to move -1 step forever until it touched the side of the screen. And as I'm watching this do this project, my mind is blown, right? You could hear the brain matter shifting in my head going, holy smokes, I can see the curriculum in what you're doing, where I thought I was just going to create this coding club after school and we're going to have a lot of fun. And we totally had fun. But I watched these students translate this baby left and right across the screen by manipulating an X value. And they coded the baby to flip when it touched the perimeter of the screen, right? And I said, how are you making the poop missiles work? Because I don't understand. And they said, it's so simple. At any given time, the baby is broadcasting its XY coordinate as it's moving, right? And so when the poop missiles decide they're going to shoot at random, they request the location of the baby. Then they plot themselves at that coordinate point, and they translate to the bottom of the screen. Now, the students obviously weren't using those terms, you know, translation, but I was, because that's my curriculum. As a grade 7 and 8 math teacher, I recognize the geometry in this process. And I said, so the poop missiles appear at the XY coordinate of the baby at a set location, and then they translate to the bottom of the screen. And they're nodding, yeah, that's totally how it works. And I said, okay, how do they go down? And I knew what the answer was going to be, right? And they all kind of stared at me like, really get with the program. We told you how the baby moves. We change Y to -1, and we put it in a loop. And that makes the poop drop to the bottom of the screen. And my mind was completely blown. So they had created variables because they wanted the user of the game to actually get a score. So every time you caught a poop missile at the bottom of the screen, and here I am doing the gesture in my house, like you can all see me, I'm making the gesture of a moving paddle. Every time you catch a poop missile, the score variable would increment by 1. Okay, so I'm watching this thing going, you guys have created this game using geometry and some algebra. Now we're talking about variables as placeholders and locations where we can store information, and we're going to increment this score variable by 1 every time you catch a poop missile. Okay, so 10 years ago, these students challenged my pedagogy because I watched them construct their own knowledge and understanding of the entire strand of grade 7 and 8 geometry in an authentic context without any explicit teaching. I observed, and we had conversations, just like Growing Success has today, but this was over a decade ago. I watched them do what Seymour Papert has been saying for 40 years. I watched them construct by trial and error and learning by taking a risk and trying something new and receiving immediate feedback on the computer. And the pooping baby, as funny as it is, changed my pedagogy and changed the way I approach mathematics up to this day, almost a decade later. Having said that, let's talk about how we can do some of these activities in our own classroom, okay? So we want to get to this place where kids are creating content in the sandbox. An app like Scratch is something I call a sandbox, where kids use block code to create content. But we can't just dump them in that sandbox and set them free. We have to get them prepared to understand what block coding is and to understand some of the fundamentals of computer science before we can sort of set them free. So I'm going to back it up a little bit. I'm going to go back to procedural writing, because ultimately that's what coding is. It's a set of instructions. So here's an example procedure I would have pitched to my class about 5 years ago. And I would have said to my grade 7 and 8s, we're all going to write a procedure for making toast. Everybody has to write this thing. We're looking at the format of your writing, you know, numbered steps or bulleted lists. We're looking for transition words, things like that. And I realized back then that I didn't quite understand why I was asking all kids to do the same thing. I was exploring the notion of equity and the fact that kids probably make toast a little bit differently than everybody else, and certainly differently than the way I make toast. And I have no idea where people keep their toaster. I know where I keep my toaster. So let's look at this procedure for making toast from this linear sequential standpoint. Okay, step 1, get the toaster, plug it in, find the bread. Before I go any further, can you give me a quick check mark if you're a language arts teacher and you have to teach procedural writing? Because I can skip over the example completely. So far, we are 100% language arts teachers. Green check mark if you teach procedural writing. Yeah, everybody does. That's kind of what I expected. So here's a hack you can take back to your classroom tomorrow, if not Monday. So we're talking about how to make toast, and I'm trying to figure out how to engage all learners, and I'm trying to figure out how to scaffold and differentiate this lesson where I want all kids to do the same thing. But ultimately, my job is to teach procedural writing, and I really don't care what the procedure is. I don't care what the context of the procedure is. It's the form of writing that I'm teaching. So one day, sitting in class, a student says to me, what happens if we don't have any bread? Or what happens if the power is out? And this throws a whole monkey wrench into that linear procedure. You know, what happens if we have no bread? And I start thinking about this from a conditional statement standpoint, right? What happens if we have no bread? Well, then another student says, well, then obviously we have to go and get bread. Well, the notion of going to get bread is a procedure upon itself, right? And depending on where this bread location is, whether it's at the store or grandma's house, or you're going to steal it from next door neighbor, that procedure is going to look differently to different kids based solely on access and where they live. And we would talk about, you know, what would you do if the power was out, and kids got really creative and started to say things like, well, I could make toast with a candle, or I could make toast with a lighter, or whatever they had at home, whatever their own experiences were. And it really made me think through a computer science lens that I can actually teach conditional statements through a traditional procedural writing task. So now, picture that procedure that you make your students write and think about it through the lens of what if. So if we have bread, then we can make toast. But if we don't have bread, we have to go and get bread somewhere. And I started to think about this traditional lesson of teaching procedural writing from a linear perspective, and I thought, how do I make it so multi-dimensional? How do I start using the word algorithm instead of procedure? I mean, they are truly synonymous. But one, in my mind, procedure is so linear, and algorithm is so multifaceted, three-dimensional, and really allows students to explore their own spatial skills because they have to consider different perspective. And so now I'm thinking about purpose and audience. I'm thinking about perspective. I'm thinking about the equity piece of what these kids are doing at home. And I thought, okay, I have to change how I teach language arts, and I'm going to do it by teaching a computer science lesson on conditional statements. And it's an unplugged activity, and I really haven't changed anything that I was doing in my practice. And actually, I used the Big Bang Theory as the hook. So I'm sure a lot of you have seen this. If you haven't seen this, hopefully Susan can post this into the chat room. Here's the video I used to hook the kids with the algorithmic writing we are going to do about making toast instead of the procedure. So the video is, Susan's got the link there, which is fantastic. It's only about 3 minutes long. Have a look. It's a lot of fun. And Classic Sheldon is right. It's a great video you can use to teach your kids about writing algorithms versus writing procedures, which again are very synonymous. They're just sort of three-dimensional in nature, and there's rooms to move out into different directions. So I'm going to clear the check marks. And if you could, when you're done watching the video, come back, hit the green check mark so that I know you are back and we can continue with the slides. So the link is posted in the chat box. It's a fun little quick video. Have a look at what an algorithm is, the algorithm for finding friends according to Big Bang Theory, and hit the green check mark when you return. I'm going to mute my mic so that you don't get the background noise. Don't be alarmed. I'm just going to go off for about 3 minutes, and I will see you in a few.
Just to clarify, because I know there are a few new people, the link on the slideshow does not work, so use the link in the chat that I just posted. Brian clarified that. I'm just saying it again, just in case.
I've seen that video dozens of times, and I still laugh every single time. We're at about 24 people say they're finished, so I'm sure the other people are just finishing up now or doing other things at home. So I'm gonna continue now. So I want you to, here's hack number 1. Okay, so think about a lesson you've done with your class in procedural writing, and think about how you can look at it through an if, then, else conditional statement lens. And we're talking about variables here. So I'm going to pick on Monopoly because most of us, I think, are familiar with Monopoly. So let's think about being in jail in the game Monopoly. So if it's my turn and I'm in jail, and those are both variables on that screen. So my turn and in jail are variables. If those are both true, then I will roll dice. And roll dice is now a function or a module or a procedure or an algorithm upon itself, right? And start using those terminology with your class instead of just procedures. Start using these other terms. I find they're way more engaging, and I find by the time kids get to grade 7 and 8, as soon as I say procedural writing, they kind of tune out. But if I say writing code or writing an algorithm, they're totally engaged, and the task is the same. So if roll dice is a procedure, then if rolled doubles. And rolled doubles is another variable, and it's either going to be true or it's going to be false. If it's true, then I will leave jail, which is another procedure or another function. If rolled doubles is false, then I stay in jail. And staying in jail is a very simple procedure, but a procedure nonetheless. I'm not even touching that one, Colleen. You're all by yourself on that one. So here, that's good. And it's being recorded. So here's my first hack. How do I take a traditional procedure like brushing teeth? Let's pick on, say, a grade 2 or a grade 3 health lesson. And here's what you can do. You're going to split your class into groups based on their own strengths, weaknesses, and next steps. And instead of every student in the class writing the same procedure for brushing teeth, you're going to break them into mini modules or mini functions. And so you might have a group of 3 or 4 students write a procedure to simply get the toothbrush. And they're going to talk about where they keep their toothbrush, because believe it or not, families and kids all keep their toothbrushes in different locations. And then you're going to have another group of students that might write a simple procedure for getting toothpaste. And they might have to consider the fact that we're out of toothpaste, and they might have to consider writing a little sub-module or a sub-procedure. That would involve getting toothpaste from a family member next door, down the road, or even the store, right? And you might scaffold or differentiate for a group that needs a little bit extra help or extra time, and you might have them write a very simple procedure for the physical task of brushing teeth. And it might literally look like move brush right, move brush left, repeat 30 times, right, for that physical, actual brushing of the teeth. You might have another group then write the procedure for cleaning the toothbrush. You might have another group write the procedure for physically putting the toothbrush away, and another group might write the procedure for actually putting the toothpaste away. So the same lesson I've always done with my class, I have now completely scaffolded and differentiated without any additional prep time. And as a class, we're going to write the algorithm for brushing teeth. But as small groups of students, they're all going to write individual modules that are scaffolded based on their abilities, right? So remember, I'm still teaching the form of procedural writing, but I've wrapped it in this coding lens, this coding language. I'm calling it an algorithm, and I'm completely scaffolding it and differentiating it, because I know some of these modules are going to be way more challenging than some of the other ones. We good with that one? Any questions? Anything anybody wants to add at this point? That was my first hack a few years ago, and I thought this is a great way to do an unplugged activity in a language arts classroom using a lesson I've always done. And it doesn't even have to be brushing teeth, right? It doesn't have to be health. It could be the point guard on a basketball court has to determine certain scenarios and certain outcomes and make a split-second decision based on variables as they receive a pass. It could be something in a history classroom about talking about, the War of 1812 and different scenarios and different procedures that some of those soldiers might have had to experience and go through. But it's still just simply writing a procedure or writing code, like a set of instructions to complete a task. No questions. You're all so quiet. Okay, so at this point now, if you do this activity tomorrow or even next week, you've really hit upon many of the fundamentals of computer science, and you haven't actually done any coding with technology. I mean, we're coding procedures and we're coding algorithms. We've talked about conditional statements, if then else. We talked about loops, which is just efficiency and automation. We talked about variables, which is a great mini lesson in algebra as well as science when you're talking about independent and dependent variables. And we're talking about syntax, right? What does code actually look like? Is it block code? Or are you writing an actual language like we do in our actual English classrooms when we're writing language? Okay, I want to back it up ever so slightly and talk about computational thinking. This is a fairly new term that is the umbrella of everything I'm talking about with regards to coding and looping and spatial sense and playing with Minecraft and abstract thinking and all of that stuff. So Jeanette Wing wrote a paper in 2006 when I was actually playing with Scratch for the first time, making the pooping baby with those awesome kids. And she defined the term computational thinking. She said, computational thinking is no longer just a skill for computer scientists, like it always has been. Computational thinking is the synergy of technology and the human mind. And now, I view computational thinking as a kid deciding they're going to make a green screen as a solution to a task a teacher has pitched. I don't feel that computational thinking means we're going to make every kid in our class make the same green screen video. I want them to think about the tools that they have access to, and I want them to think of a way to solve a problem that I've pitched to them. And in my mind, that's what computational thinking is. It's not me telling them to use a tool. It's them determining the right tool for the right job that's completely relevant to them in what they hope to accomplish. Does that make sense? Computational thinking. It's a very daunting term, but it really means to solve authentic problems using our own ideas combined with the power of the technology and the tools that we have access to. It might simply be creating in Minecraft. It might simply be organizing data in a spreadsheet and displaying it. Just getting caught up on the chat. Susan says 5 of you have your hands up. If you have a question, I'm going to hit the clear button. If you have a question, feel free to ask it now. Raise your hand, hit the green check mark, send something into the chat box. Okay, so this next slide I cannot take credit for, and it's so powerful. And I'm just going to put it up. It's so Twitter-worthy, so I'll just wait while you tweet that one, because really it's self-explanatory. Go ahead and send a tweet on that one. Right? If we want to improve math scores in Ontario and we want to reduce mathematical anxiety, then perhaps we should look at computational thinking as a skill set to enable our students in mathematics to land in the middle of that Venn diagram and be the ultimate problem solvers that we want them to be. When I look at this slide, I always think in my own practice on the right side, how many of those criteria have I banned in my classroom? Have I fought with in my classroom? We fight. I fought gaming. Put the games away. We're not gaming right now. We have to write this note in science class or something along those terms. How many of those things in that right column do we struggle with in our own classrooms, rather than totally embracing them and having kids find the link between counting, arithmetic, algebra, geometry, and so on, as well as simulations and data mining and gaming and algorithmic reasoning. So algorithmic reasoning is what we've already talked about with the example of brushing teeth. Sarah says, typo on the Microsoft quote. Thank you for pointing that out. I will make the change on that. And Colleen says, we're all busy processing new information. I know. But really, so far, we've touched upon things that we all have access to and things that we can do in our classrooms right away. So I hope that gives you a great insight into something you can take back without having to sign out an iPad cart or having access to a computer lab. We can touch upon a lot of these computational thinking strategies in a traditional procedural writing English class, I guess. But I want to back it up even further and talk about the research and the history behind this movement, because it started a long time ago. And we have a couple of questions. So Anik, go ahead. Either turn a mic on or fire it into the chat box. And Victoria, I see, what is data mining? Data mining would be something like, and I'm not going to pick on a corporate identity, but one we're all familiar with that likes to make money off of ads, whether it be YouTube or Google ads, if you will. So those types of organizations would look at data, and when they say mine it, they're sort of extracting it, looking for trends. And trends might be demographic, trends might be age group, trends might be type of technology you're using. They're looking at data and they're extracting information and considering bias so they can formulate decisions, conclusions, I guess, from a marketing standpoint. So it might even be as simple as having kids do a survey at school, and by data mining it, they're sort of extracting the trends in it. And it might be gender, it might be demographics of the community, it might be religion. All of those things are factors, of course. Does that make sense? Okay, great. Awesome. Okay. Thank you, Susan, for getting caught up on those questions. I think we're good. Yeah, the hands turn off by themselves. Okay, so back to Seymour Papert. Man, I have been studying his work for a very long time. Unfortunately, he's somebody I never met in person. Fortunately, I have met many people that have worked with him, alongside him, and under him. It's still difficult to speak about Seymour Papert in a past tense. He passed away this past July, but he made a lot of predictions about education and educational technology in the 80s and 90s. Things we're seeing now, he stated, he made claim to about 30 years ago. One being, of course, the role of the teacher is to create the conditions for invention rather than provide ready-made knowledge. Now, he said that before the age of information. He said that before the internet, before we all had access. And he said the computer would radically change things we do in our classroom and things we should do in our classroom. And unfortunately, he didn't gain the traction, I guess, he deserved back then, largely in part to the fact that technology was so expensive while he was pushing it, right? Now, he started the MIT Media Lab, which I'm sure many, many people are familiar with. And because Mary Kay said turtle, we have to talk about logo. I mean, Seymour Papert developed the very first block coding language, what we would call by today's standards a block coding language, where he said if students could demonstrate a math task and replicate it on the computer and make the turtle do it, not only had they grasped the geometric concept through geometry, they'd also applied it, right? If we want kids to find the perimeter of a room through a kinesthetic activity, then they should walk it themselves and use their own footsteps as a unit of measure. So far ahead of his time that I just have to share this little excerpt. The video that I want you to see now is a group of students in the 80s playing with robots and drawing shapes on paper on classroom floors. Things we now see on Twitter with Spiro and things we now see on Twitter with Dash and Dot, he was doing 30 years ago with Logo, and he believed we should teach kids to construct their own knowledge of mathematics through trial and error, through risk-taking, and through immediate feedback from the computer. So please watch this. Do him the justice that he deserves. It's a fantastic video, and it just shows you how far ahead of his time he really was, like somebody had mentioned. Again, I'm going to mute my microphone. It's a relatively quick video. If you could just give me the green check mark when you're back, I will have a great understanding of where we all are. So off I go until then. Okay, it looks like just about everybody's back. I had never seen that video in 2005 when I was making the pooping baby on Scratch with those kids, but everything he said about them constructing their own knowledge of mathematics in an authentic context through trial and error, and exploring in the whole inquiry-based model of education we talk about today, I remember experiencing that and not understanding it, but knowing I was onto something that was so powerful with those kids. So kudos to him. Obviously, like I had mentioned, the first block-based coding language was built on geometry, so a great way to teach geometry and properties of geometry in an authentic context. But I want to bring it full circle, both in my own learning and to where we are today. So Seymour Papert sort of started this movement at MIT, late 70s, early 80s, and there's some of you had mentioned it in the chat already. Mitch Resnick was one of his students. Dave, you're so right. He was way ahead of his time. So Mitch Resnick followed in Papert's footsteps and also still to this day works at MIT. And he was the big idea person behind Scratch. Okay, he was the one that said we're going to bring Logo, I guess, into the 21st century back in 2003. And they had developed it under the principle of 4 Ps. So they say passion, play, projects, and peers are the reason that you should be on Scratch. And we're going back 13, almost 14 years ago now when Scratch first hit. So even by today's standards, that's a little bit old. It's starting to gain traction, of course. I'm sure many of you are aware of it based on the check marks that you gave at the beginning of the webinar. But it's a block-based coding language where kids can link code together without writing syntax in a sandbox, so they can create content based solely on the limitations of the tool itself. And there aren't many. I think you're only limited by your own creativity as a teacher and a learner and a student in that sandbox. But I want to fast forward it even further than Mitch Resnick and his work at MIT, because Mitch Resnick, of course, has students at MIT. And 2 of them were Eric Silver and Jay Rosenbaum, who decided that under the guidance of Mitch Resnick, they wanted to bring Logo and Scratch and coding and computational thinking to the physical space. So under the guidance of Mitch Resnick, they took to Kickstarter, and they decided they were going to kickstart the Makey Makey. So they created this prototype that allowed you to connect alligator clips to physical world objects that would control and move digital objects that you create in the Scratch platform, because Scratch is based on a keyboard input. So they believe everyone is creative, inventive, and imaginative, and that everyone can create the future and change the world. So they've dedicated their lives to making an easy-to-use invention kit that they named Makey Makey. And I want to share with you the Kickstarter video that they posted a couple of years ago, because they were actually successful with this campaign, which is fantastic, because now we have a physical, tangible piece that we can engage with in our classrooms, have kids inquire about circuits, which is our grade 6 science curriculum here in Ontario, but also inquire about conductors. I learned through playing with the Makey Makey that the clay we have in our art supply rooms is not a conductor, but name brand Play-Doh is. And it was my students that actually discovered this. And it led to a whole explanation research project about the salt content of Play-Doh and why it was a conductor and the clay wasn't. So I'm very fortunate, I feel very fortunate that we have the Makey Makey to sort of extend the work of Papert and Mitch Resnick into that physical space. So have a quick look at what this thing is capable of if you're not familiar with it. It's a really, really, really cool tool, very engaging for kids, and requires absolutely nothing in terms of installation. So Susan has gone ahead and posted the video, and Chipmunk Brian is back, which means somebody's bandwidth is hogging. We'll blame Blackboard, because it's definitely not my bandwidth, of course, right? Oh, I'm back. I'm back. Okay, great. Okay, well, just as I'm back, I'm going to hit mute. There's the video. Check out the Makey Makey Kickstarter campaign. It's awesome. I have a whole variety of these Makey Makey kits, and the kids absolutely love them. So I'm going to mute my mic. I'll see you again in 3 minutes. Hit that green check mark when you're back. I always think about the floor piano, you know, in Big with Tom Hanks. I actually had a couple of students try and code that last year and recreate it, which I thought was totally cool because you can extend the wires. You can extend those alligator clips. So we went out and we bought really cheap speaker wire at Home Hardware, and we had split it down the middle, right? Because speaker wire actually comes in a left and right channel, so you get twice as much length as you want. We had kids build an app that would play a piano on the floor, and we put tinfoil down, and we stretched it all the way down the hallway. It was a super fun, engaging activity. One of the other big game changers for me last year was, how do I reinvent my bulletin board space? So traditionally, the bulletin board space has been that area where I've put up those look-fors, right? When you have the really important people that come through and look for things in your classroom. So the honor walls and the word walls and things like that. I thought, well, I don't have those anymore. We've moved into the cloud. We hang out in an LMS, so I'm not printing, right? My word walls are digital and my honor walls are kids' portfolios now. So how do I reinvent that cork, you know, the cork board? So it was actually kids' idea. They said, well, we're going to build circuits with speaker wire, and we're going to connect it to a Makey Makey, and we're going to put tinfoil buttons on the bulletin board. And this was a year ago now, so we're pushing on to Halloween. And I said, what are those tinfoil buttons going to do? And they said, we're going to make a haunted bulletin board. So we're actually going to code a soundboard in Scratch. We're going to download some spooky sounds that are going to be triggered by keyboard input. So like the up arrow would be a howl, and the down arrow would be a vampire, and things like that. And we're going to make circuits. We're going to connect it to tinfoil. And so when you touch the bulletin board, you're going to hear those sounds because we're going to wire it to a Chromebook, and we're going to connect it to speakers. And I thought, now that is computational thinking. Right there. These kids decided they are going to create a solution. They wanted to build this thing using circuits, which again, I teach a grade 7-8 split class, so they just come out of grade 6. Grade 6 circuits. We're going to use circuits to build this massive space on our bulletin board, and we're going to bring the bulletin board to life. When they were done, and create, right, and collaborate, and all of the Michael Foulon 6 C's, and you know the 21st century skills we talk about, STEM, and all of the engineering stuff. So, I'll get to your question there, Stacy. The biggest piece to this story is the staff hogging the bulletin board and pushing the buttons. It wasn't kids. It was the staff coming around going, how did you make this thing work, right? And as the kids are telling the teacher, I start hearing explanation. I start hearing my language curriculum again. I'm hearing oral communication. These kids are explaining how they built circuitry on a bulletin board connected to a Makey Makey. And I thought, that is how I make my bulletin board space interactive and engaging. So back to the question, Stacy, are there programs with Makey Makey? How do you connect alligator clip to a sound? The Makey Makey is simply a keyboard interface. So when you plug it into the computer and you close a circuit on the Makey Makey connected to, let's say, up arrow and the ground section, the computer thinks you just pushed up on the keyboard. Okay, so when you bring that into an application like Scratch, in the Scratch environment, you would have it say, when up arrow pressed, play sound. And that's where the kids have put the sound in. And so connecting it to the Makey Makey, connecting it to tinfoil, creating a circuit when you push the tinfoil button, Scratch thinks you pushed up on the keyboard and then would play the corresponding sound that the kids had created in the soundboard. And I'm happy to share all these lessons. I've actually written about these activities. They're on my blog. I'll totally share them at the end. There's so much potential with the Makey Makey, and I'm happy to do a follow-up after with just on Makey Makey. I'm happy to talk about it. There's so much activity we can do with the STEM stuff. Okay, so I'm going to move forward on that, but we'll revisit it after, and I'll share with you all of my content. Everything that I've shared tonight and everything that I've researched, I have for everyone to take. So let's go back quickly to my second hack, another unplugged activity in math. We talked about literacy, we talked about computational thinking, and I just want to talk about activities that you can do tomorrow and Monday, Tuesday, all of next week in a geometry classroom. So there's two pictures on the screen. The picture on the left is Kristen Wydine's classroom from Windsor, Ontario. She's a good friend of mine. The picture on the right belongs to a teacher named Jessica Konechny from my own school in Chatham, Kent. And they both wanted to participate in the Hour of Code, and they didn't have access to technology. So they reached out and they said, how can I do the Hour of Code? I want to be involved. What can I use? So we created this program. So Kristen on the left, she went through her geometry curriculum under location and movement, and as a class, they created Pseudocode. So you can see there it says RT90 or FD4. I believe this is LT90, FD3. So that's right, forward, left, forward. So she used her location and movement strand within geometry to create a pseudocode with her students. And then they put it up on, the smartboard or a whiteboard or a blackboard or whatever. And she split her carpet into a grid, right, like a battleship, Cartesian plane. And she placed objects in certain cells of the grid. And she had kids then write a procedure, right? We're writing procedures in math now, but we're calling it an algorithm. We're blanketing it as coding, so it doesn't sound like procedural writing. We're writing a module, we're writing an algorithm in math class. Just like we've done in language, students, like we've written procedures for so long. We're going to do one, we're going to look at it like this. Now I need you to navigate your way through this grid on the carpet using the geometry, sorry, she didn't say geometry, using the code that we created as a class. And so again, without any additional prep work, she's completely scaffolded and differentiated for her students because she's putting objects in different spaces on this grid. Some, of course, are more challenging to access than others. But again, without any additional prep work, every one of her students is able to feel success because they can write a procedure or a module that will access an object at a certain location within the grid. Now the picture on the right, Jessica Konechny is a brilliant grade 1 teacher, certainly smarter than I am. She did the same thing. She dissected her geometry strand and they looked at location and movement and they created symbols based on that math curriculum. And then she pulled out, she had access to one iPad, and so she connected the iPad to the projector, and she wanted to use the iPad as the teacher, just like Seymour Papert had mentioned in that video. So the iPad was going to give the feedback. The iPad was going to tell the kids if they're right or wrong. The kids are going to learn through trial and error. So she projected the app called Lightbot. And in the app Lightbot, you have to move a robot around a screen by linking code together. And you have to put the robot from point A to point B. And so because she only had one iPad, she decided her kids are going to build the terrain from the app they see that's projected using linking cubes. So I think about the spatial reasoning skills involved in this task because these kids are seeing a flat image projected on the screen that is interpreted as 3D, but then they have to actually go and build it with linking cubes. And then they had to use their symbolic code to move that brown block you see on the right side. They had to move that to the blue block on the far left side. And when a group of students thought they were finished, they would go up to the iPad and they would try it. And if they were right, the app would show them stage 2, and they would have a more challenging level. And if they were wrong, the app would sort of guide them through the process and try and help them out and give them feedback. And it freed up her time to consolidate with other kids in the class that needed that additional one-on-one time. So I took these ideas. I said, we have to start with geometry. But what does this look like in all grades? Okay, so I created this slide. This is not any computer code at all. It's what I call geometry pseudocode. And I'm not a primary teacher, and I have a little bit of experience in junior, but this is sort of what I picture geometry looking like in these different age groups. So as a class, we can create a pseudocode based on our own geometry, regardless of what grades you teach and without any access to technology. But we can start talking about coding Friendbots. So hack number 2, location and movement. You could put students in pairs, where one student is the programmer or the coder, and one student is the robot. And the robot's job is to do nothing but follow instructions given by the coder, who's then going to write a procedure or an algorithm. And again, without any additional prep work or any differentiated instruction on the teacher's part, you can scaffold it by having some groups do a really challenging algorithm. It might be go deliver this message to the principal. It's very kinesthetic. Kids are moving through the hallway. And it might be very simplistic, like you might have 2 students code each other to actually just go and get a drink from the water fountain located in the hallway. Every student has the opportunity to feel success. Every student gets to engage in geometry, location, and movement, and every student feels like they're actually coding. You have scaffolded it in such a way that some of the modules are more challenging than some of the others, but completely kinesthetic for kids to do. But it also allows for that wide walls, low floor, high ceiling we talk about, the enrichment opportunity, because some kids might look at it from an efficiency standpoint and talk about automation. At least, that's my experience, of course, right? In grade 7 and 8, maybe not in grade 1, but if they're talking about efficiency in grade 1, send them my way because I want to meet them. But it's certainly a space where you can extend the task without doing any prep work at all. So I think there's a lot of value in that. And you're sort of bringing geometry to an authentic context, right? And so what I did with this as a grade 7 and 8 teacher is I fired up the graph paper because I had photocopied a stack of grid paper from years past, that I thought I would burn through. And I could fire up a grid on my smartboard as the bell's ringing and draw some arrows and say, okay, folks, I need you to now code the robot to follow the arrows that you see on the smartboard. Here's some grid paper. Go, right? And the kids would all sort of follow that task. But I could then extend it, and I could say, okay, we're going to make a game now. I'm going to show you the same grid. Here's the same code that we've created as a class. I need you to go unlock the chest. What does that look like? And because there's more than one way to solve this problem, you've got the multiple entry points, you've got the wide walls theory, the low floor, high ceiling. You've got the opportunity for all kids to feel successful because they're going to be able to solve this problem. Some solutions will be more efficient than others, and that's totally okay. At the end of the day, you can then have students go and actually create their own games using simple grid paper. So fantastic. Susan, totally, totally, I know. I need to go spend more time in primary, I really do. I want to move outside of geometry. So Scratch is geometry by default. What you do with Scratch is what makes it so awesome. So here's an example where old school traditional Brian would have kids tell me about quadrilaterals as a grade 7 and 8 teacher. I want them to tell me that quadrilaterals have the sum of the interior angles is 360 degrees, and I want you to tell me about properties of trapezoids and yada, yada, yada. And I typically had them do it through textbook work and worksheets. And I thought, what, I don't need them to do properties of 30 different trapezoids. How can I rethink this question? So I started to ask them about, how do you know what the properties of the trapezoid are? So then I would project a procedure, right? I would project code like this from the Scratch platform, where it says in blue there, move 300 steps, point in direction 0, wait. Move 150 steps, turn negative 90 degrees, wait. Move 300 steps, turn negative 90 degrees, wait. Move 150 steps. And I would project this, and I would say, what does this draw? How do you know, right? More importantly than just yelling at me, you know, that it draws a rectangle, how do you know it draws a rectangle? And I want the kids to tell me, well, I see 4 90-degree angles, I see 2 sets of parallel lines, because that's ultimately what I want them to do, is I want them to describe those shapes with regards to my own 2D measurement curriculum. But after this, I would then say, okay, now I want you to go and create the scratch code that's going to draw 2D shapes. And again, we've got that wide walls, low floor, high ceiling, multiple entry point kind of a task, because some students might draw a very simple shape, like a triangle, and it might even be an equilateral triangle, so the angles are all the same. But some students might take my algorithm or my procedure, and you know, those kids that want the enrichment activities, and they might try and draw a 3D shape using linear procedure, using a flat surface, using computer code to draw a 3D shape. So I think about the abstract thinking and the computational thinking and the critical thinking and the spatial sense that totally goes into a task like that. So if you take these ideas back and you just simply play tomorrow, it's Friday, you want to get your feet wet, you've touched upon geometry. Here are the big ideas, regardless of what grades you teach in the province of Ontario, for the geometry, location, and movement strand of math. But more importantly than that, I feel strongly that these activities are so rich in nature that it allows us to focus on the process of mathematics, which is found at the beginning of every grade level in our curriculum document. And the word computational strategies exists in our document that was written in 2004. Now, our interpretation of computational strategies has obviously changed, but the fact that the term was used back in 2004 when I was first learning about the pooping baby sort of blows my mind. And I also think that focusing on the problem-solving process and the process of mathematics allows us to do some really creative and innovative things with regards to the Ontario learning skills. And I feel very strongly that the learning skills are an indicator of the grades on the inside of the report card. If you look at the front page of an Ontario report card and you see those E's and G's, you know they're A's and B's on the inside, right? And if you see those S's and those N's, you know what the grades are on the inside. So I feel very strongly that if we focus on learning skills, then the rest might fall into suit, right? Little Johnny's mom would come to me and say, you know, I want him to improve his math. Can you give him some more math homework? Well, I often wonder if it's his initiative or his organizational skills that is resulting in a poor indicator in his math learning and not the quantity of math he's actually exposed to. So if we focus on these rich tasks with observation, conversation, anecdotal notes, really rich activities that allow students to all feel successful, then we can focus on the problem solving, the mathematical process, and the learning skills in Ontario. I have to share one example that pushed my pedagogy. I was teaching probability a few years ago, and I was having kids flip coins and making a T-chart and tally the experimental probability, because it's my job as an intermediate teacher to teach them the more times they run the experiment, the closer the experimental probability gets to the theoretical probability. So if you flip a coin a bajillion times, the expectation is your results would be 50-50. But we all know if you flip a coin 3 times, it will never be 50-50. It's 100% one way, or 33% or 66%. So I had handed out change, and I had kids flip these coins and do this T-chart, and it was a gong show, right? I had students in my class that already understood theoretical probability, so they weren't going to flip the coin because they already knew and they were faking it. I had other students that were throwing money at each other, and I didn't know how else to teach probability. And at the end of the class, a group of boys approached me and said, can we create a simulator? And now I'm going back to the Venn diagram I had shared earlier. They didn't use the word simulator. I'm using the word simulator for the purpose of this webinar because they use computational thinking skills to solve a problem in my world. They said, we want to make this, they want to make a coin flipper app, right? So I'm going to call it a simulator for you folks. So they created a simulator for me. In a Scratch environment, they had it pick a random number from 0 to 1, and if it was 0, they showed heads on the screen, and they changed a heads variable by 1. And if it was tails, they would show tails on the screen, and they would change the tails variable by 1. and it blew my mind. It took them about a week to accomplish, and they all came into school early before the bell had rang and said, "It's done, we got to show you this thing." And I hate to generalize kids and stereotype kids, but if I had to put them in a category, these are your disengaged, sort of level 2, grade 8 boys heading to the applied stream, okay, just to give you a sense of their profile, I guess. So they'd come in early and say, "Whoa, what are you doing? You know, why are you in here early before school? I mean, I'm so happy you're here. It's cool. What's going on?" And I said, "We finished it. We finished the coin flipper." And I said, "No way. Like, let's see it. Let's fire this thing up. What's it going to do?" And I said, "You have to put it on the smartboard, and we're going to flip this thing 1,000,000 times." And I chuckled and, drinking my morning coffee, half awake, and I looked at them and I said, "Yes, we are," right? So we threw it up on the smartboard computer and set this thing to flip 1,000,000 times because they duplicated the code. They'd thrown it into a loop. They'd fired up this turbo button, and they said, "You as the user can determine how many times the simulator is going to run, and because it's a computer, it's going to run really, really fast." So the bell rings and the rest of the class comes in. For the first time in my experience with these boys, the whole class was watching their work on the smartboard, right? These boys had never had their work projected for other students to see, and they were just grinning from ear to ear. And we do a lot of rotary at our school. So as this thing is running, I dedicated the smartboard computer to the coin flipper for the whole day. As this thing is running, they were asking to go to the washroom. They were asking to get a drink. They were making up excuses to leave other classrooms because they wanted to see what this coin flipper was at. And it blew my mind. By the end of the day, it actually didn't reach 1,000,000 flips, and I was sad. But it reached 750 some odd thousand coin flips, and it was 50-50 to about the 12th decimal place. And I just looked at these boys and I said, that is experimental probability meeting theoretical probability, and you just created a simulator to teach me and you about the law of large numbers. And it was totally a game-changing experience for me. They extended it by using a Makey Makey. They actually had physical objects in the classroom that would work as coin flippers. We invited our superintendents to come in, and they were touching, bananas on a desk to flip a coin on their coin flipper simulator. And then they were telling the superintendents about the math, because I said to them, we're building a simulator, but you have to tell these people the curriculum. Tell the superintendents about experimental probability, about variables, about the law of large numbers. And they did. And I never would have got that out of this group of kids through a textbook method. So a whole slew of application that we can do under coding. Let me fast forward a bit because we're running out of time. Back to Jeanette Wing and computational thinking. The Internet of Things. This is a scary and sort of intimidating fact, even in my own world. By 2020, we're going to have more objects connected to the Internet than people, right? That means your fridge might Snapchat you when the water filter is dirty. It means your stove might Instagram you when the oven's at room temperature or oven temperature. And it means for the first time in human history, we're going to have more vehicles connected to the Internet than not, right? Self-driving cars alone will eliminate thousands of jobs, but thousands of new ones are going to be created to support these new technologies. And if you read any of the information and the sources that are out there, including the Globe and Mail article I shared with you earlier that was printed today, we are sort of in a skills gap crisis. There's going to be more positions in industry that require computational thinking skills than qualified people to actually fill them. And this is where I'm kind of torn. I feel very strongly that coding and computational thinking should be taught in schools, but I don't want it taught based solely on the short-term gain of entry into industry, I think. Currently, we don't have a curriculum on coding and computational thinking, so currently we typically don't give kids a choice as to whether they think they will want to be a professional programmer in the future or not. And so I want to expose as many kids as I can to coding and computer science so they can decide for themselves if coding is right for them. I don't teach writing in my classroom with the mindset that every kid will be a professional author. I would absolutely love it if that were the case, but that's not the reason I teach that subject area. I don't teach basketball in my gym class because I think everyone's going to be in the NBA. I would absolutely love it if they did. It's not the reason I teach coding and computational thinking either. I just want it to see its fair chance as a 21st century literacy and a 21st century skill in today's day and age. So where can you start? Well, based on the diagnostic from the beginning, it sounds like so many of you are finished with the hour of code, so that's great. I feel like a lot of you are already in that sandbox, and if you're not, please email me and reach out to me on Twitter, and I'm happy to help you on this continuum that I've created. So I get emails on a regular basis about this notion of where can I start, I want to start. And so in my mind, we've got this number line, this continuum, and on the far left, we have what I call bot coding. And that's your Lightbot app, it's your Codable app, it's your Hour of Code app, where the kids get exposed to block-based coding, but they're told what to do, right? And then they have to go and do it, and then the computer tells them if they did it right. And if they did it right, they move on to another level that's a little bit more challenging. Now, there's a lot of critical thinking involved in creating those procedures and those algorithms and those kinds of bot coding apps. But ultimately, we want to push kids into what I call open space coding, which is using block-based coding in a sandboxed environment so kids can create content to demonstrate their own thinking and their own understanding of curriculum content that we do have. I don't often head into the syntax environment as an elementary school teacher because we don't have a coding curriculum here, so it's not my job to teach JavaScript or to teach Python. So I typically hang out in that sandbox that I call open space, and we really want to get kids to create content using block code after we've exposed them to what block code is. And as Erica points out, some of those apps and things under collaborative, when I made this slide a couple of years ago, I shouldn't have named it collaborative, but it's stuck and I've never changed it. I think the whole process is collaborative, but when I say the collaborative stage, I mean because of people like Seymour Papert, we now have block-based coding languages, right? Computer scientists wrote code in the 50s, 60s, and 70s in ones and zeros in what we called machine language. And we've progressed, and we've built software on top of machine language using syntax. And we've progressed from syntax to building technologies using a block-based coding environment. So when I say the collaborative stage, it means we've got real computer scientists that are creating tools to allow future coders to code in a more simpler way than what they are used to. There's a lot of predictions that say in the very near future, many developers won't actually need to know syntax because we're going to strictly move into a drag-and-drop based environment where real syntax coding can be left to the computer scientists of the world that choose that as a profession. But the people that want to create content using computational thinking skills will simply use the drag-and-drop based apps for that. So, on that note, we are at 8:57, and I have a screen share slide at the end, but I won't do that. I'm going to post into the chat box. If you're interested in anything I said, including my slides, including some tutorials, including how to get started, what do I do, where do I go, where are the links to math, where are the links to literacy, help, I heard everything he said, now I want to try it. I've compiled all of my resources and posted them at hourofcuriosity.com. In my mind, it's kind of a next step beyond the hourofcode.com or the hourofcode.org, which is a great entry point, but certainly not a destination. So if you head over to the hourofcuriosity.com, there's a lot of research there about spatial sense and abstract thinking and Minecraft and coding and augmented reality. If you're interested in the lesson plans about Makey Makey and creating interactive bulletin boards and things like that, I blog about that stuff at brianaspinall.com. Those are pretty well both of my two go-tos in terms of where I post all of my content. See, and we taught Susan something new. So that is always a win. I will chalk that up to a win. At this point, feel free to jump in. Anyone else?
Okay, I'll jump in. Very funny.
Oh, there are people there.
Oh, isn't that weird? We're all here. I think, you know what? I think this is an enthusiastic crowd. I've been following the chat as you've been talking, and there's all kinds of goosebumps, and I'm excited. This is going to be the best year ever. I don't know if you saw all those comments, Brian, but that is all thanks to you and your enthusiasm.
I'm excited to go. I'm excited to go back through that. But even cooler, I have 54 Twitter notifications right now on top of the chat box. How amazing is that for the province of Ontario?
And they're not all me. That's awesome. Okay, I'm going to advance to the next. Oh, there's a couple.
Yeah, no one can leave yet. We need feedback so that these things continue.
Yeah, exactly. So for those of you that are new, particularly to the OTF Connect sessions, they really value your feedback. And when you log out of this session, and you log out simply by closing the window or closing the application, you will automatically get an immediate link to the feedback survey. And it's just quick. And they really want you to do it because A, it helps them to plan for future sessions, and they're in the process of planning winter, spring right now. And B, it also drives funding, believe it or not. So, you know, all of your enthusiasm, if you can pile that into your feedback survey, that would be great for OTF and great for Brian as well. So thank you for doing that. This is the very beginning of a new season of OTF Connects. It's their 4th year, and it's growing and growing. Many of the sessions coming up are sold out, so we would love to have you join us for another evening. Here's the link that will take you right out to the calendar, so you can check out some further OTF Connect sessions. You can also just Google OTF calendar, and it's all there. The Ministry of Education, once again this year, is subsidizing teachers who take AQs in the areas of math, technology, and kindergarten up to $450. So if you go to the OTF website again, you will be able to find that. You can also just Google OTF subsidies for AQ courses, and I'm sure you'll find the answer. There you go. Brian's teaching a course in January. He's doing one right now, and he's doing it again through ETFO, which is awesome. So you could get a subsidy and have most of your course paid for. That would be fantastic. There's also financial literacy, which is another area that OTF has webinars in this area. There's a conference coming up, and it's advertised right here. So once again, Brian, that was an enthusiastic and engaging evening, and I think the audience is captured. And I'm going to thank you for that, and I'm also going to thank all of you for your enthusiasm and your participation. I'm going to stop the recording now, but both Brian and I will hang around for a few minutes if you still have some questions. So this is our official end.